Hi, NA Physics, it's Mr. Neff again. Let's talk about concave spherical mirrors for a second time, and let's, at the end of the video, give that punchline to the doctor that tried out for the play but broke his leg. On the last video, we talked about a concave mirror, but we had an object that was inside of the focal point. That gave us this image that was virtual, upright, and magnified. Now, I want to see what happens whenever you move on the other side of the focal point. So I've got an example like that too, but this time the object's outside of the focal point. So look at, I've got a 2 centimeter high object situated 15 centimeters in front of a concave mirror. So right away, I can see that my DO is going to be a positive 15 centimeters. At the same time, I can see that my HO is going to be a positive 2 centimeters. Why positive? Well, when I measure that, it's going to go up from the principal axis. It says that this concave mirror has a radius of curvature of 10 centimeters. Remember that the radius of curvature, C, is going to be twice what the focal length is. So if C is 10 centimeters, and in this case positive because that's out here on the positive side of the mirror, then that means the focal length is going to be a positive 5 centimeters, also on the positive side of the mirror. So that focal point is right there where it's marked in the picture, and here is that focal length, positive 5 centimeters. So 15 centimeters, there's 5, there's 10, 15 looks pretty good where it is. If I wanted to show you that 15 centimeters, well, that 15 centimeters would be from that vertex all the way out here, and so there's that DO of 15 centimeters positive because it's in front of the mirror. Now, they want us to use the ray diagram to find the location and the height of the image. Now, the order of steps exactly the same as what I've done a few times in these videos. First thing I'm going to do, I'm going to draw the parallel ray. And so I'm going to come from the flame and I'm going to go parallel to the principal axis like so. And then I'm going to reflect through the focal point. And so here I come reflecting through the focal point, and this is actually going to look a lot like what I did on the last video. There we go. Parallel ray. Now the focal ray is the one that leaves and goes towards the focal point. Now, on the last two examples, the concave one and the convex one, I couldn't actually get through the focal point. I just used the focal point to line up the ruler. This time, look, I can actually get through the focal point, hit the mirror, and now reflect out parallel. And so that's going to look, I'm trying to do a very good job lining it up parallel. There it goes. That's going to go parallel like that. So now you can see I have two outgoing rays, but look at the difference this time. For the first time, I actually have the two rays physically crossing, whereas on the last example, let me go back to that. See the outgoing rays, outgoing rays? They were never going to cross. Here, they're never going to cross again, but they are crossing right there at that spot. That's a big difference. That's going to say I'm going to get a real image. Now, I can also draw the chief ray this time. Remember I said that sometimes just based on your picture, the chief ray is not very easy to draw, but this time it works well. I can go candle flame, center, and I'll draw this one right here, and it will reflect exactly back along itself. There it goes. And look how that intersects at that same spot too. So I have 3 light rays crossing right there. Just like always, where they either seem to be crossing or where this time they really are crossing, that's going to be the image of that candle flame. So there's that candle flame right there. And now the base of the candle is going to be on the principal axis. And so I'm going to draw that candle there like so. Now notice something. This time, for the first time, I have a real image. It's real light that is crossing there. And in fact, you could put your hand or a piece of paper or something, and you could actually focus that image on that screen. So it's real light crossing. It is inverted this time. And for this one, you can see that the candle was much bigger. The actual candle is much bigger than the images. So I'm going to say that this one is reduced. So when you're inside of the focal point, you get a virtual upright image on a concave mirror. Whenever you're outside of the focal point, you get a real inverted image. Turns out that the center of curvature is the place where you go from being magnified to being reduced. Since we're even outside the center of curvature, we're seeing reduced. Now I can show you that even better on the simulator from our friends at Pearson Prentice Hall. So I can have a concave mirror here, and I'm going to make it so that it's not quite so round. I'll move that center out like so. Now look at something like this. I can take the object and I can have it inside of the focal point. And see something. Inside of the focal point, I'm getting a virtual image because the way that the rays reflect, they're never going to cross out here on the positive side of the mirror. So they're just going to seem to cross behind the mirror. And so I'm getting this upright virtual image. It's also magnified, and I can't do anything about that. I can't get it to not be magnified. In fact, here, can you see that as I get farther and farther away, it gets more and more and more magnified to the point where it's so far back in there I can't see it on the simulator anymore, but it is there, and it's humongous. When I get to this point where I'm right at the focal point, you can see that those two rays are parallel, and so you might say, well, that will mean that they're never going to cross. Optically, it means that they actually cross out at infinity. So this would form a humongous image, and it would be all the way out at infinity, and we're going to see that come up later on when we talk about lenses. Now, if I bring the thing on this side of the focal point, now you can see that they will cross, and I'm going to make the mirror a little bit smaller in focal length. And so you can see as I get from this side where I'm getting this humongous image to the other side of the focal point, now those two are going to cross. Even though they're not crossing on the screen, you see over here that this red one and this purple one, they will cross over here if this were just long enough. And so there would be an image over here somewhere. And if I bring this far enough out, you can start to see the image. So the focal point is an important spot. On the inside of the focal point, the image is going to be virtual, and it's going to be upright. On the outside of the focal point, the image is going to be real, and it's going to be inverted. Center is going to be an important spot too. The center is going to be a spot where you're going to either go from magnified, where the image is going to be bigger than the object, to reduced. And I haven't gotten outside of this center just yet. When I get to the center, you see that the DO, which would be from here over to the solid red one, and the DI, from the vertex to the orange one, lighter red one, is going to be the same. Now, if I keep on going beyond that, now you see image is still real, but it is reduced this time. So back over to our example, they asked us to find the location and the height of the image. Well, the location of the image is going to be right here. I'm going to say that is my DI. What would you guess that is? Well, here's +5, here's +10. I'm in that ballpark. Maybe the DI is about +8 centimeters. I don't know if that's really right. In fact, I'm going to back off on that 0.0 because I don't think we can have that kind of precision. I'm not very sure about this, but I'll bet when we finally calculate this, it will come out pretty close to 8. And then the height of the image, I'm going to say, is this thing right here. Now, we just saw from the simulator that anytime you're outside of the focal point, outside of the center of curvature, the image is going to be reduced. And so this was supposed to be 2 centimeters right here. And even so, I think our picture looks pretty good. 1.5 maybe for height of the image. Time will tell when we get back to the math. So if I were going to summarize all of that for us, here is our concave mirror. And if you put the object in this zone from the focal point to the vertex, you're going to get this kind of image. You're going to get that virtual upright enlarged image. And that was like the first example that we did. If you go in this zone from the center to the focal point, you're going to get a real image. Notice anytime you're out past the focal point, you get a real image. It's also going to be inverted, and it's going to be enlarged whenever you're in this center to focal point zone. After you get outside of the center, it's going to still be real and inverted, but this time it's going to be reduced. Right at the center, you're going to get an image that's real and inverted and the same size, and right at the focal point, you're going to get an image that is out at infinity. And so that covers our concave mirrors for today. Hey, did you hear about the doctor that broke his leg while he was auditioning for the play? Luckily, he still made the cast.